Okay, good evening, students. So today we'll discuss about the propagation of nerve impulse. So before that, let me summarize what we have discussed yesterday. Yesterday we have discussed about the origin of resting membrane potential. We have seen that it is produced and maintained by membrane selectivity. That means how a membrane acts as a semi-permeable or selectively permeable membrane. The difference between those two we have seen. And another one is sodium potassium ATPase pump, which I'm going to discuss now. And the third thing is it is produced and maintained by the permeability of membrane to potassium ions as well as sodium ions and other ions. So all these result in a resting membrane potential. How you are going to define a resting membrane potential? It is the difference in charge. For example, this is extracellular fluid, this is intracellular fluid. This is the difference in charge on either side of the plasma membrane, which constitutes the membrane potential. And if the membrane is not stimulated, we call it as a resting membrane potential. In generally, what happens is the difference between the charges means the electrical potential across the cell membrane occurs due to only ionic gradient, which is created due to difference in ionic concentration of substances between intracellular and extracellular environments. This relative static membrane potential of a resting quiescent means not stimulated, unstimulated cell. Quiescent means it is somewhat uh, what we call resting membrane. Quiescent means. So this resting unstimulated cell is what we call it as the resting membrane potential. And coming to the role of ions, the potentials result from movements of ions across the membranes, because of which there is an unequal distribution of ions on both the sides of the cell membrane, which moves the ions from high concentration to low concentration by diffusion, which results in the electrical gradient as the ions move from like charge to opposite charge. And this happens through certain channels until equilibrium on both the sides is said to be reached. This equilibrium potential is for each ion is determined by an equation called as Nernst equation. The Nernst equation suggests that it is for any ion, it is the membrane potential at which the ion is in equilibrium. Nernst potential is nothing but it is the potential for any ion, okay, at which the ion is in equilibrium. I've told you before only the chloride ions and sodium ions, when they are equal in on either side of the plasma membrane with respect to the charges or with respect to the number, with respect to the concentration, whatever it may be, there is a movement of ions even in equilibrium. If 5 ions go this side, again as there is a change in the electrical potential, 5 ions come this side. So the net moment is said to be 0. So according to Nernst potential, there is no net movement of the ions across the membrane. It is always 0. Okay, and I have already told you when compared with potassium ions and sodium ions, when we compare these two, there are more potassium channels in plasma membrane than sodium channels. Hence, potassium is considered as the major cation which contributes towards generation of resting membrane potential. And this is the equation for Nernst equation. A is equal to RT by Fz in x1 by x2. Here, R refers to gas constant and T refers to absolute temperature, and E is the potential difference across the membrane, and F is the Faraday's constant, and Z is the valence of ion. And what you have to remember is this thing, mainly the definition. There is another one that is called as Goldman-Hodgkin and Katz equation. Nernst equation is related to any ion, that means one single ion. Whereas here, Nernst equation cannot be used if a membrane is permeable to two different ions. So this can be explained by another equation called as Goldman-Hodgkin and Katz GHK equation. Let's see, there is a transmembrane movement of three ions, sodium ion, potassium ion and chloride ion, which contribute to the membrane potential, and this equation explains the potential that is generated when two or more different ions are involved. And the equation is like this, where these are constants and time, and it is related to the concentration of potassium ions on outside by O refers to outside, I refers to inside by inside. Likewise, concentration of sodium ions outside by inside, and the relative concentration of chloride ions inside and outside. Okay, and another one which we have discussed yesterday is the Gibbs-Donnan membrane equilibrium, where one non-diffusible ion present on one side, like organic phosphates, organic sulfates, negatively charged proteins that we have seen in yesterday's class. So those are the non-diffusible ions which influence the diffusibility of diffusible ions, so that there is an unequal distribution of ions on either side, resulting in membrane potential. And this Donnan membrane equilibrium results in what we call it as generation of resting membrane potential. So these three things we have to remember. One is Nernst equation. I'll be sharing this PPT with you. Second one is GHK equation, and third one is Donnan membrane equilibrium. In addition to this, we have to get acquainted with certain other terms with relation to membrane potential. What these are the depolarization, hyperpolarization, repolarization, and overshoot. So at the end of class, you'll be able to understand what these are. But for the time being, let me define these one by one. Depolarization is nothing but it is a decrease in the potential difference between the inside and outside the cell. For example, it is 70. So if it decreases, then it is called as depolarization. Opposite to which there is hyperpolarization. It is increase in the potential difference on either side of the plasma membrane. Then repolarization. It is restoring back a membrane which is resting membrane potential gets depolarized, and bringing it back again to the resting membrane potential is what we call it as repolarization. Returning it to the resting membrane potential from either direction is called as repolarization. It can be from outside to inside, or it can happen even from inside to outside. Whatever it may be, it is repolarization only. Then overshoot. When the inside of the cell becomes positive due to the reversal of the membrane potential polarity, and inside generally we have seen that there is positivity outside, negativity inside. When the inside of the cell becomes positive due to the reversal of the membrane potential polarity, we call that as overshoot. So these are the main terms associated with this concept. And when we see the origin and propagation of nerve impulse, you're going to get information about these three things. So let me explain this. Before that, I have to explain the sodium potassium pump first. Okay, sodium potassium pump has two functions. It is responsible for maintaining the volume of the cell. The first function is to maintain the volume of the cell. That means whenever the cell volume increases, it sends out sodium ions to outside so that water also goes along with it and the volume is said to be brought back to normal. Okay, and the second one is because of the operation of this pump, there is potential difference on either side of the plasma membrane, which results due to unequal distribution of ions. Thus, this potential difference results in electric potential, and hence we call this pump as electrogenic pump. So, sodium potassium pump produces, it is responsible for maintaining the volume of the cell, and at the same time it generates electrical potential or membrane potential, hence we call it also as electrogenic pump. But actually, what is a sodium potassium pump? Sodium potassium pump is characterized by the following features. First of all, it is a carrier protein. It is a carrier protein. Second thing is, it acts as an ATPase. The same protein acts as an ATP. That means it can break down ATP to ADP and inorganic phosphate. And it operates in active transport mechanism. That too, when the requirement for movement of ions from low concentration to high concentration is required. That is active transport. So these are the main features. In addition to this, it can be this same carrier protein can be phosphorylated or it can be dephosphorylated, which brings about a change in the shape of the or conformation of the carrier protein. So let us see what happens actually here. So we see that there are so many lipid molecules in a plasma membrane. So the hydrophobic lipid molecules are arranged like this. And here there is a sodium potassium pump. And this sodium potassium pump is a carrier protein which encloses a channel. It is a carrier protein which encloses a channel. So this channel, when it is not operating, it gets closed on the outside, and it has two binding sites for potassium ions and three binding sites for sodium ions. So here there are three binding sites for sodium ion and two binding sites for potassium ions, and it is closed outside. So this is thus a plasma membrane. Okay, now what happens is, now when the sodium potassium pump operates, sodium ions that are present inside in low concentration, they have to be transported to outside from low concentration to high concentration. Okay, and in so doing, they also transport potassium ions in the opposite direction. Hence, we call it as a sodium potassium pump. For this transport of sodium ions from low concentration to high concentration, it requires the breakdown of energy, and this ATP, this carrier protein, as said before, it also acts as an ATP. Yes. Now what happens? These sodium ions now go and bind to the three binding sites. After binding to the binding sites, this acts as an ATPase now. This acts as an ATPase. Thus, it breaks down ATP and releases energy. It releases energy. At the same time, it forms ADP diphosphate and inorganic phosphate. And now what happens is this protein, this protein which is said to be bound to three sodium ions, okay, and having two binding sites for potassium ions is opening on the other side. Now it has a binding site for phosphate also. So once the ATP is broken down, once the ATP is broken down, the phosphate that is released here, the phosphate that is released here, now it binds to the carrier protein. Now what happens? It gets phosphorylated. So the sodium potassium pump gets phosphorylated. So this phosphorylation and the energy that is released during the ATP breakdown is now responsible for opening up of the channel on the other side. How this happens? This happens by it bringing about a change in the conformation of the carrier protein. So far it is opening inside. Now there occurs a conformation change. Now it opens on the other side. So now what happens is, so it starts opening on the other side. Okay. So this is the plasma membrane. Now its shape is changed. What happened now? It opened on the other side. As soon as it opens, previously there are three sodium ions bound here. Now all the three sodium ions start moving to extracellular fluid. So after phosphorylation, its conformation is changed and it opens to the other side. Now, due to this, what happens? Sodium ions are sent out. How many? Three sodium ions are sent out. Now, what happened? This carrier protein is exposed to the outside where there are potassium ions, and here there are two binding sites for potassium ions. So these potassium ions now jump inside and they bind to the binding sites. So that potassium is now attached to the carrier protein. And what happened here, it is still in phosphorylated form. Now what happens is this phosphate is said to be removed. That means now it undergoes dephosphorylation. After the sodium ions attach, its ATPase activity is enhanced. It breaks down the ATP, releases ADP, inorganic phosphate, and energy, and the phosphate is attached to the carrier protein, which brings about a conformation, that is change in shape of the molecule. Thus, the channel opens to outside, by which three sodium ions are sent out. As soon as the sodium ions are sent out, the potassium ions now bind to the binding sites of the carrier protein. As soon as the potassium ions are binding, the phosphate is released and we say it gets dephosphorylated. So the dephosphorylation brings the what you call this one to the same configuration where there are only potassium ions inside and sodium ions are already released out. And what happens? This conformation releases the potassium ions inside. How many? Two potassium ions are released. Thus, for every three sodium ions that are sent out, two potassium ions are sent inside. Because of which, what happens? There is a more positivity outside. This is the plasma membrane. Because of the operation of sodium potassium pump, there is more positivity outside. How many? For every 3 sodium ions, let us say there are 300 sodium ions went out and 200 potassium ions came inside. So there is more positivity outside. In addition to this, there is equal distribution of chloride ions which we have seen yesterday. They are almost equal on both the sides. In addition to these two, there is a third ion, that is nothing but the organic anions like phosphates, sulfates, etc., which cannot be transported at all because there is no carrier protein, there is no mechanism that can transport a phosphate, negatively charged phosphate ions or sulfate ions, so that there are more negatively charged ions inside, thus the inside gets negativity. So because there is a non-diffusible ion present on one side, the diffusibility of the diffusible ions is said to be influenced, resulting in a potential difference, a charge difference or voltage difference on either side, resulting in an electric potential on the membrane, which we call it as membrane potential. Thus, Donan membrane equilibrium is what is responsible for the establishment of membrane potential. Because this membrane is still not stimulated, we call this as a resting membrane potential. So thus, by the operation of sodium potassium pump, a resting membrane potential is developed. When the resting membrane potential is developed, there is positivity outside and negativity inside. Why positivity is outside? Because there are more positive ions due to the functioning of sodium potassium pump. Why negativity inside? Because there are more organic anions than the positive ions in inside. So with respect to extracellular fluid and intracellular fluid, there is positivity outside and negativity in the intracellular fluid on either side of the plasma membrane. Such a membrane is a resting membrane. Such a membrane is a resting membrane. And if you insert an electrode, if you insert an electrode inside, you get only negative reading, and this is measured and found to be minus 70 millivolts. So the first thing is resting membrane potential, which is originated and its value is minus 70 millivolts. Now what happens? Now we have given a stimulus. The stimulus can be of three types. The first type is said to be, it can be chemical stimulus, like any alkaline or acidic solution that is put on your tongue. And the second one is a thermal stimulus, hot versus uh, cold temperatures. And the third one is said to be physical stimulus. If any such stimulus is given, what happens is there occurs a disturbance on the site where the stimulus is given. Okay, so let's see what happens now? So when the stimulus is given, when the stimulus is given, we say the membrane gets depolarized. Okay, membrane gets depolarized. How this takes place? This takes place because of the, again, the movement of ions only. So we have seen there are more number of sodium ions accumulated outside. This occurred due to the operation of the sodium potassium pump. Now there are more diffusible sodium ions outside which try to come inside, for which they require a change in the membrane permeability. So a slight stimulus on the nerve cell membrane brings about this slight change that is required. And now what happens? The membrane permeability for sodium ions increases. The sodium ion permeability increases, and through sodium channels, not through the sodium potassium pump, through sodium channels, sodium ions enter inside. Sorry, through sodium channels, sodium ions enter inside. So when sodium ions enter inside, so due to sodium increase in sodium permeability, sodium ions enter the intracellular fluid. Already potassium ions are there, already sodium ions are there. Now sodium ions are there. Now what happens? There is increased positivity inside. So due to this, positivity occurs inside. As sodium ions are sent inside, there are negatively charged ions are outside, and they establish a negativity outside. So there is a reversal of charges, reversal of charges occurring at the site of stimulus. This reversal of charges is called as depolarization. So the first thing that occurred is resting membrane potential, where there is positivity outside and negativity inside. So positive, negative. So when you give a stimulus, the sodium permeability increases and sodium channels allow the sodium ions to enter inside, and this results in what we call it as a reversal of charges at the point of stimulus, not everywhere, only at the point of stimulus only there is a reversal of charges. So here what happens, these two are said to be normal because that is not stimulated, but this region is stimulated, the center, so that there is a reversal of charges. So this reversal of charges results in what we call it as a depolarization, where there is negativity outside and positivity inside due to, sorry, these are negatively charged. So there is negativity outside now and positivity inside due to a stimulus given at the site. Now there are sodium ions positive inside and potassium ions positive inside. Both are present inside. Now because they are said to be positive ions, they tend to repel each other. So one of them has to go out because there is no more positivity inside and negativity outside. In order to bring a balance, one has to go. So which one goes, sodium or potassium? We have seen that potassium channels are more in number, so that potassium ion starts moving outside. So now what happens? There is a movement of potassium ions to outside. So at the point of stimulus, at the point of stimulus only, the potassium channels open and the potassium moves to outside, because of which at the point of stimulus again there is what we call positivity outside and negativity inside. This we call it as repolarization. Okay, that means in the resting membrane state there is resting membrane potential where there is positivity outside and negativity inside, and we call this as a polarized membrane. We call this as a polarized membrane. Why we call it as a polarized membrane? There is a positive pole outside and negative pole inside. There are two poles, opposite poles. It is a polarized membrane. When you give stimulus, sodium permeability increases and it results in depolarization where there is negativity outside and positivity inside caused by reversal of charges mainly at the point of stimulus only. And after that, these positive ions repel each other. Out of these two, as potassium ions are said to be having more permeability, they start moving outside. So because of the movement of potassium ions to outside, at the point of stimulus, only again at that point of stimulus only, what happens? Here, there is re-establishment of positive charge outside and negative charge inside. So after repolarization, there is positive pole outside and negative pole inside, and we can call it as a polarized membrane. Okay, so the polarized state is said to be re-established. We may think like this, but that is not the case. Why? In a polarized membrane, there is positivity outside and negativity inside, but the positivity is caused by sodium ions that are present outside. In polarization also there is positivity outside and negativity inside, and this positivity outside is caused by potassium ions that are present outside. Okay, and I've told you before only there are more positive, there are more potassium ions, potassium channels inside the plasma membrane. So once the potassium starts moving out, more and more number of potassium ions are moving out. Now what happens here? So more number of potassium ions than required are being sent out. So potassium ions are sent out. Now what happens? There is positivity outside already established, repolarized, negativity inside, it is re-established. That means repolarization has taken place. Even after repolarization, the what we call transportation of potassium ions still continues. That means inner negativity further increases. This we call it as hyperpolarization. The inner negativity further increases, which we call it as hyperpolarization. So when they have measured, the scientists have measured the what we call potential here, a resting membrane is found to contain a potential of resting membrane potential of minus 70 millivolts. And here, when the same electrode is placed inside during depolarization, because there is a positivity inside, it further decreases. The resting membrane potential changes to 40 millivolts. Now, when the potassium ions move out, the resting membrane potential value of minus 70 is restored during repolarization. Even after repolarization, the potassium ions are still moving out. What happens? Inner negativity further increases and it becomes 90 minus 90 millivolts, which we call it as hyperpolarization. So both repolarization and hyperpolarization are caused due to the movement of the stored potassium ions in large numbers from inside to outside. So every time we say and sodium potassium evaporates, three sodium ions are sent out and two potassium ions are sent inside. Why this should happen? That should be the question in your mind. And you may think that because there are only three binding sites, there are three binding sites for sodium ions and two binding sites for potassium ions, this is happening, isn't it? That is what we uh, infer and confirm for that question. But actually what is happening here, there are more potassium ions outside and sodium ions inside, and this sodium ions now have to compensate for the more number of potassium ions to inside outside. Why? Because it has to be brought back to polarized state. Whenever you give a stimulus, the stimulus will be taken only the membrane by the membrane which is resting membrane. Only resting membrane will respond to the stimulus. A depolarized membrane will not respond. A repolarized membrane will not respond, and even a hyperpolarized membrane will not respond. Why? Because when a stimulus is given, what change occurs? There is a change in the sodium permeability. So, for depolarization to take place, sodium ions should be outside. But in all the cases, sodium ions are inside. In that case, stimulus will not bring about a change in the membrane potential. So only resting membrane will be excited, but not a hyperpolarized, depolarized or a repolarized membrane. Now what happens now? Now operates the sodium potassium pump. So what is sodium potassium pump? The sodium potassium pump, when it operates, it sends three sodium ions outside. It sends three sodium ions outside. Why? It has to compensate for the extra potassium ions that are sent outside, and for which, against which, two potassium ions are sent inside. Thus, what happens is the resting membrane ionic status is re-established. This is what happens due to the operation of the sodium potassium pump. Now we can say that now we can say that there is sodium outside and potassium inside, and now this is a polarized membrane ready for a second stimulus. And all these things are happening only at the site of stimulus, and there are so much activity taking place here. A polarized membrane is depolarized, followed by repolarization, followed by hyperpolarization, again coming back to the normal polarized state. So all these activities which bring about a change in the potential difference along a nerve fiber at the point of stimulus, resulting in activity. Hence, we call this as an action potential. So, thus, this results in the generation of an action potential. So, what does action potential refers to? It refers to all the activities that take place at the point of stimulus when when there is a change in the activity of the nerve cell, with respect to which there is a difference in the what we call potential difference on either side of the membrane, from polarized state to depolarized state to repolarized state to hyperpolarized state, finally again to polarized state. All these events occur in a cascading manner, one by one, so not cascading, in a sequential manner, resulting in action potential. So this is how an action potential is generated at the point of stimulus. That means if this is a nerve cell membrane, that means axon with dendrites and telodendrites, this is the point of stimulus. There is positivity outside and negativity inside on either side. Okay, and now at the point of stimulus, the first thing that happens is reversal of charges, depolarization, negativity outside and positivity inside on both the sides. And again repolarization, positivity outside and negativity inside, repolarization. And it further continues with hyperpolarization. And finally it results in the bringing back the normalcy by the operation of the sodium potassium pump. Thus there is a positivity outside and negativity inside. All these events are taking place only at the point at the place of stimulus, not elsewhere. That means action potential is generated only at the site of stimulus. So this stimulus has to be sent out from this neuron to the next neuron, from that to the next neuron, and ultimately it has to reach the brain. From the receptor, it has to reach the center. Okay, that means it has to be propagated. So the propagation can occur in this direction or in this direction. So whenever the stimulus occurs, the wave of physiological activity can be bidirectional. It occurs in both directions. But scientists say that it is unidirectional. That means it is orthodromic in direction. So what do you mean by this? So this wave of physiological activity goes this side and reaches the dendrites, and it goes this side and reaches the telodendrites. And from the telodendrites through synapse, it reaches the dendrites of the next neuron, but not to the telodendrites of the neuron that is present before that. So, even though it passes on both sides with respect to the same neuron, but when this impulse has to be transmitted to another neuron, it is always from telodendrites to dendrites, but never from dendrites to telodendrites. Thus, we can say that it is unidirectional. So, how this unidirectional, what we call uh, flow of nerve impulse occurs, we are going to discuss. So, if you have any doubt up to this point, ask me. Otherwise, we'll discuss about the propagation of nerve impulse. Any doubt? Okay, can I ask you a few questions? Hmm? Okay, done. So, the first question is, so what is the value of the resting membrane potential? Minus 70. What is the value of depolarized membrane? Minus, not minus. In, inside becomes positive. There is reversal of charges. So it is plus 40. The third question is how depolarization occurs. When a stimulus is given, there is a change in sodium permeability. This is what we have to uh, identify in the objective options that are given in your question paper. Okay, sodium ions enter. Okay, how they enter? They enter because there is a change in the sodium permeability. When this shows, when actually the sodium change in the sodium permeability occurs, only when a stimulus is given. Okay, so thus it is always depolarization is always stimulus driven. Then, what happens during repolarization? What happens? Not the value I am asking about. What happens during repolarization? So after the sodium potassium, sodium change into sodium permeability occurs, sodium ions go inside. There is a ripple of positive charges and potassium ions start moving outside. So there are two terms associated with this. This term during depolarization we call this as sodium influx. What you have to write here is sodium influx, and opposite to this we call this as sodium efflux. Okay, so depolarization occurs due to sodium influx caused by a stimulus, and repolarization occurs due to potassium efflux, that is movement of potassium ion from ICF to ECF. Now, what is the value of repolarization? Repolarized membrane is again minus 70. Then, after repolarization, there is a process called as hyperpolarization. Why hyperpolarization occurs? No, it is the potassium starts going outside. The potassium efflux takes place during repolarization, which continues. Even it reaches minus 70 from plus 40 to again it reaches minus 70, but still as the potassium permeability is more, as more potassium channels are opened, there is more potassium efflux, which results in hyperpolarization, the value of which is minus. So after hyperpolarization, what should happen? There is re-establishment of resting membrane ionic status. So how the re-establishment of resting membrane ionic status takes place? What happens after hyperpolarization? Hmm? What happens after hyperpolarization? Sodium potassium pump operates so that sodium ions are sent out, 3 sodium ions, and potassium ions are sent inside, 2 potassium ions. Thus, the resting membrane ionic status is said to be re-established. All these things happen only at the point of stimulus. Now let us see how the propagation takes place. So coming to propagation of action potential, a theory was established and proposed, that is called as local circuit theory. Okay, so how the propagation of nerve impulse is explained? It is explained by the local circuit theory. So what is the local circuit theory? Here, this is the nerve fiber. There is positivity outside on either side and negativity inside. Okay, and we have given a stimulus here at this place. Now what happens? Depolarization takes place. Due to depolarization, sodium influx takes place, and now there occurs what we call reversal of charges on either side, which results in depolarization. Now, before repolarization happens, there is a reversal of charges here. That means there is a potential difference from minus 70 to plus 40. So electrical potential is said to be generated. So this electrical potential now acts as the stimulus to stimulate or disturb the permeability of the adjacent regions which are in resting state. So this is the resting membrane, this is the stimulated membrane. So this stimulated region now, where the potential difference causing the electric potential now starts stimulating the other one. Now what happens? On either side of this there is a reversal of charges. There is a reversal of charges. That means depolarization of the adjacent membrane takes place. As the depolarization of the adjacent membrane is taking place, the scientists say that here already has what has happened? Depolarization has happened. Once the depolarization has happened, now there occurs repolarization at the same place. So, as depolarization of the adjacent membrane is being continued, now repolarization of the first place where the stimulus is given takes place. Now what happened? Here at the point of stimulus it is repolarized, followed by hyperpolarization, followed by again operation of sodium potassium pump. All these events are taking place here. But by the time what happened here, the adjacent sites are said to be depolarized. So now here occurs there is a change in the electrical potential. This stimulates this one. This region stimulates the adjacent region. So this stimulates the adjacent region. Now this gets depolarized. This gets depolarized again. By the time it gets depolarized, this region gets repolarized. So thus here local circuits of current are being established. This depolarized membrane depolarizes the adjacent one. By the time it gets depolarized, the other one gets repolarized. Thus, local circuits of current are established all along the nerve fiber. So, from the point of stimulus, these local circuits of current are said to be propagated. In one word, we can say that what is actually happening here? When we give a stimulus, the membrane gets depolarized. Okay. Then what happens? This depolarized membrane now depolarizes the adjacent membrane. By the time it gets repolarized. Now this depolarized membrane again depolarizes the adjacent membrane. So wherever you see all along the length of the nerve fiber, there is just you can see one depolarization wave. Starting from the stimulus, on either side, a depolarization wave is said to be transmitted, which we call it as nerve impulse. So, nerve impulse is nothing but propagation of a wave of depolarization from the point of stimulus in either direction up to dendrites on one direction, up to telodendrites on the other direction. But from that neuron to the next neuron to pass through, it happens from only telodendrites to dendrites, but never from dendrites to telodendrites. Thus, we say, though with respect to the same neuron it is bidirectional, but the propagation to the next neuron is always unidirectional. So, thus, the formation of local circuits of current, local circuits of current is said to be the reason behind the propagation of nerve impulse. And we just can simply call it as nerve impulse is nothing but a wave of depolarization. When we say wave of depolarization is passing on continuously, the depolarization is followed by repolarization, hyperpolarization, and sodium potassium pump operation. All these events are happening on the other side, the same thing. In other words, this region action potential is generated. Once it is repolarized, this region gets repolarized again. This region gets repolarized again, hypolarized again. That means action potential is generated again on either side. So this action potential is transmitted on either side. So what actually propagation of nerve impulse is? We can simply define it as the transmission of action potential along a nerve fiber. This is the simplest answer. We can also call this as the transmission of a wave of depolarization along a nerve fiber. So both of these answers or options refers to the same thing, that is transmission of or propagation of nerve impulse all along a nerve fiber by the formation of local circuits of electrical currents or electrical potential caused due to the potential difference, again in turn again caused due to the movement of ions. So finally the conclusion is nerve impulse is always caused by the movement of ions when a particular stimulus is given. This happens when the membrane is said to be non-myelinated, whereas in a myelinated nerve fiber there is a myelin sheath. So there is a myelin sheath and these are called as nodes of Ranvier. Nodes of Ranvier. So there are so many nodes of Ranvier all along the length of the axon or nerve fiber. The region between two nodes of Ranvier is called as internode, and internode is the region which is non-excitable, whereas nodes of Ranvier is the region where the lipid membrane is absent, the myelin sheath is absent. This is excitable. So what happens when you give a stimulus? When you give a stimulus, at the point of stimulus, what happens? Previously, it is positive outside and negative inside. Wherever you see positive outside and negative inside in a resting membrane. Now, when you give a stimulus, what happens? There is a reversal of charges, resulting in negativity outside and positivity inside. So, this results in what we call it as depolarization. So this depolarization again, what does it do? It depolarizes the adjacent membrane. What is that adjacent membrane? Another node of Ranvier. So local circuits of currents are produced between two adjacent nodes of Ranvier. Thus, this much distance is covered during by the local circuits. So when you see a non-myelinated nerve fiber, the action potential is traveling all along the length of the nerve fiber by formation of local circuit. Whereas in case of a myelinated nerve fiber, it jumps, it jumps from one node to the other node. Thus, it goes in a faster way. As it jumps, in Greek we call it as, or in English we call it as saltations. This type of conduction is called as saltatory conduction. So in a non-myelinated nerve fiber, as the impulse transmitted from one node of Ranvier to the other node of Ranvier, which are the excitable points for stimulus response, here we call it as saltatory conduction. So with this we come to the end of what we call propagation of nerve impulse. So this propagation of nerve impulse is nothing but the propagation of the action potential. This action potential has certain properties. One is the strength and duration of intensity. It is explained by two terms, rheobase and chronaxy. What is rheobase? It is the minimum strength of stimulus when applied for adequate time produces a response. Previously, we have told you that until threshold stimulus is reached, it cannot respond at all. For example, it is 50 millivolts is the or 5 millivolts is the what is threshold stimulus for the nerve to get depolarized. If you give 4.5, according to all or none law, it will not respond at all. But Rio base says that if the 4.5 is given for some duration, let's say if it is given for 2 milliseconds or 3 milliseconds or 4 milliseconds. So if it is given for a certain duration, the value may reach the threshold value. then it gets excited. So the minimum strength of stimulus, the minimum strength of stimulus when applied for enough time to produce, that means so that it reaches the threshold stimulus to produce a response, is known as reobase. So reobase is related to what we call here the stimulus given for a particular time. Next, what is chronaxy? The minimum duration, this is the time, that is with respect to strength given for a period of time. Now this is with respect to duration given with a particular strength. So the minimum duration for which a stimulus of double the strength of reobase is applied is called as chronaxy. Muscle fibers are found to have faster chronaxy value than nerve. So here the difference is it is related to strength given for adequate time. It is the time, the duration of a double strength of reobase value. That is the relation between these two. And coming to the second property, all or none law. The subthreshold stimulus, that means 5 millivolts, less than this. As given an example, 5 millivolts is the threshold stimulus, below which it is subthreshold stimulus. The subthreshold stimulus fails to produce a response, whereas the threshold stimuli causes the generation of an action potential, which we call it as all. That means threshold stimulus generates the action potential, it is all. Subthreshold stimulus lesser than the threshold stimulus will not generate at all, that is called as none. The third property is excitability of nerve fiber. So nerve fiber is always excitable, and this excitability can be referred to in what we call a refractory period. The refractory period is the period between two successive responses of a muscle or nerve. For example, okay, so when we plot this, you have given a stimulus here. It can be a muscle or a nerve. For stimulus, there is a response. This response is followed by again bringing back this to normalcy. So if it is a muscle or nerve, what is happening? Energy is consumed. So when you give a second stimulus again, it will not respond at all. If you give a second stimulus at this point, it may show another response. But they have found that if you give a stimulus here, after a brief interval, if you give a stimulus here, it can respond again. So here, actually, there is a brief interval between two successive responses, which we call it as a refractory period. Refractory period is nothing but we can simply call it as a resting period. This is divided into two phases. Okay, so this is the refractory period. This is differentiated into two phases: absolute refractory period and relative refractory period. What is absolute refractory period? Here, this is the first stimulus given. The muscle contracted or the nerve fiber responded. That means nerve fiber got depolarized. When it is in depolarized state, when it is in contractile state, that is muscle. If you give the second stimulus again, it will not respond at all. Why? Because a depolarized membrane can never be stimulated, as we have said before. Likewise, a muscle which is contracted can never contract again until and after it gets again relaxed. For relaxation, what is required? For contraction, ATP is broken down. For relaxation, ATP has to be resynthesized. So for ATP to be resynthesized, that requires a particular period. So this period, it will not respond at all for a second stimulus, how strong the stimulus may be. Even if you give it 10 millivolts for a 5, the muscle or nerve responds to a threshold value of 5 millivolts. Now we have given a 10 millivolt what we call current there. Even then it will not respond. So how strong the stimulus may be, if the second stimulus falls in the absolute refractory period, it will not respond at all. But by the time ATP is said to be what we call resynthesized in case of muscle. By the time resting membrane ionic status is re-established in case of nerve fiber, there is a chance for the membrane to get membrane to respond for the second stimulus. So this period is what we call it as relative refractory period. So coming to the definition of these two, during absolute refractory period, the cell is unresponsive to any further stimuli. No other action potential can be fired at this point, regardless of the strength of the stimulus. That means how strong the strength of the stimulus is, it will not respond at all because it needs some time for it to come back to the normalcy. That is what we call it as absolute refractory period. Whereas coming to the relative refractory period, during this, another action potential can be produced, but the strength of the stimulus must be greater than that of the first stimulus. So that just now it has reached what we call relaxing. It is just after contraction, it is just started relaxing. After action potential is generated, it is just coming back to the normalcy. If at that point you are going to give a second stimulus, that second stimulus should be stronger than the first one so that it can show an immediate response. And this period where it can give response to a strong second stimulus is called as relative refractory period. And next one is accommodation to slow depolarization. If a slow depolarization occurs, the voltage gated channels do not respond and no action potential occurs. So depolarization should never be slow. And there is another property called as conductivity. The action potential is conducted through the length of the neuron. The wave of action potential, they travel down the nerve fiber, that is axon. Okay, so thus it exhibits what we call it as conductivity. The conductivity differs from non-myelinated to myelinated nerve fiber with respect to the speed. In myelinated it is faster conduction, in non-myelinated it is said to be somewhat slow. And another two terms are associated with this. One is called as positive after potential and the other is called as negative after potential. So let me explain these two. Membrane potential becomes more negative than original resting membrane potential for a few milliseconds after action potential is over. That means during hyperpolarization. This we call it as positive after potential. Here positive, actually this is negative in charge. We are using the term positive because positive after potential is said to be more negative. Positive after potential, that means after action potential, after depolarization and repolarization, what happened? Hyperpolarization has taken place. That we call it as positive after potential, which is actually negative. Why we call it as positive? Because the measurement is not taken inside, it is taken by the scientist outside, and the same is said to be, name is said to be uh, continued. If it is, let us say outside is said to be plus 90. So it is measured from outside, not from inside, and we call this as positive after potential. Then opposite to this is negative after potential. After depolarization is the slow repolarization phase, which follows a rapid fall in spike potential. That means the action potential which reached its maximum height. Spike potential and extends up to a attainment of the resting membrane potential level. It is called as the negative after potential. Why it is called as negative after potential? Because there is negativity outside. Positivity due to depolarization. What happened? There is a reversal of charges. This reversal of charges is caused by depolarization. And this depolarization where there is negativity outside, and this electrode is placed outside, and it is said to be measured at that point. So depolarization is followed by repolarization. When repolarization is slow, there is negativity outside, and that negativity is called as negative after potential, which is very short duration. It is for about just 4 milliseconds, it is followed by repolarization. So this is how the action potential is generated and propagated all along the length of the nerve fiber. In the next class, we'll see what we call it. This is all this I have explained you. In the next class, we will discuss synapse, synaptic transmission. What is a synapse? What is synaptic transmission? Types of synaptic transmission, synaptic inhibition, and synaptic excitation, and the role of different ions in this particular aspect in the tomorrow's class. Okay, any doubts you can ask me, otherwise we'll close for today. Thank you.